My name's Greg Vitale, and I am, as Ryan mentioned, the National Sales Manager for Acromag Embedded Solutions. Today, I'm going to discuss what are FPGAs and why use them. This is part one of a three-part series. There's going to be part two where we'll probably go through an example design and talk about some of the advantages of Acromag FPGA boards. And then part three, we'll be discussing the Zinc UltraScale solutions and what Acromag is doing in that area. So just to give you a little topics that we're going to be discussing today, I'll give you some background on processing types, the types of ASICs, some commonly used acronyms and definitions. I'll talk about what is an FPGA, and then the development environments that Xilinx and Altera, which is now Intel, typically use. We'll touch upon the coding methods for writing your code for programming FPGAs, and then we'll get into why you want to use FPGAs, and then finally we will talk about some Acromag FPGA solutions. So typically there are four primary processing types, and I've broken them down by the CPU. This is a general purpose processor task. You've probably heard of reduced instruction set and complex instruction set computing. These are commonly referred to as microprocessors. A microprocessor becomes a microcontroller when you add additional memory on the chip and you add I/O and say specific functions like LCD control, things like that. A GPU is a graphics processing unit, and it basically renders images and video very quickly. It's known for very high performance, but also very high power dissipation. Another processing type is digital signal processors. These are high performance, but at lower clock frequencies, and they execute very complex math in parallel. And then field programmable gate arrays. These have programmable logic blocks inside of them that are unconnected, and you interconnect these logic blocks to meet your specific application requirements. These application specific requirements are programmed at power up, and the nice thing is that the FPGA is reprogrammable. I'll give you a little background on types of application-specific integrated circuits. Custom-built ASICs are purpose-built for a specific function. They're typically optimized for either low cost or high performance. And companies do custom ASICs because they have high volume requirements and either very low cost requirements or high performance requirements. The next type of standard cell is an application specific that uses a library of functions, and it is typically optimized for power, area, and performance. And it finds itself in medium to high volume applications. In the past, you may be familiar with PALs, PLDs, and CPLDs, complex programmable logic. These are smaller designs. There's a limited number of logic blocks in these, and they were used and are used today for very simple functions. They're much lower cost, and they are much more general purpose. A gate array is a fixed amount of logic resources on a die, and it is personalized to the specific application by the last 3 or 4 mask steps or interconnects. The gate array was the precursor to the field programmable gate array. So some typical and common acronyms and definitions that you would like to be familiar with when you're talking FPGAs. HDL is referred to as hardware description language. CLBs are configurable logic blocks that are inside FPGAs, and they contain lookup tables, flip-flops, and muxes. A mux is a multiplexer. A lookup table is a group of SRAM that basically allows you to map your inputs values to your output values. Intellectual property, IP cores, they can be hard cores that are physically embedded on a chip. Soft cores are HDL code that is portable and that you could take from one FPGA to another FPGA. SoC is a definition for a system on a chip. A system on a chip typically contains a processor, logic, and a variety of memory, along with ancillary processors like DSPs, which DSP stands for Digital Signal Processor. JTAG, it's an abbreviation for Joint Test Action Group, and it is typically used for debugging and programming your FPGA. A couple other terms: test access port, boundary scan register. One of the key things that you want to be aware of is hardware emulation. The definition of hardware emulation is being able to imitate the behavior of a piece of hardware that you have under design with another piece of hardware for the purposes of debugging and doing functional verification. Logic synthesis, that's converting a high-level description of a design into an optimized gate-level representation. And then finally, a bit stream. This is the file that contains the programming information for an FPGA. So simply put, what is an FPGA? It's an integrated circuit that contains programmable logic blocks, and these consist of gates, flip-flops, lookup tables, memory blocks, and then you are able to take these logic blocks, configure them how they need to be, and interconnect it through a variety of ways on the FPGA. So these interconnections are programmable, and it allows you to customize your requirement for your specific application. There's fixed amount of inputs and outputs to make off-chip connections. And as I mentioned, you typically will have memory blocks, SRAM primarily. You could add processor cores, for instance, ARM processors like the A53 or the R5, hard macros like the Microprocessor processor. And then also you can integrate soft cores into your FPGA. And IP cores, intellectual property cores, these typically have a specific function that has been tested, and you take this known good logic and integrate that into your FPGA. The key benefit of an FPGA is that its reprogrammability is a way so that you can basically try different things. If it doesn't work, you can reprogram it. If your specifications change, you can reprogram it. So it's very flexible. It mostly handles digital signals, and an FPGA could be what they call an SoC, or a system on a chip. There's a couple different types of FPGA architectures. SRAM based is the most notable, and it's basically a volatile based architecture. And what that means is that when you power down the chip, you lose the contents. So these FPGAs need to be programmed upon power up, and that's where the configuration flash comes into account with the bit stream to program these. Xilinx and Intel Altera are the two largest manufacturers of SRAM-based FPGAs. Microsemi, Lattice also produce SRAM-based. Another architecture is what they call anti-fuse based. And Actel, QuickLogic, these were two of the companies that led the market with these types of anti-fuse based architectures. These were one-time programmable, and basically they were very well known for being used in space applications. The one-time programmability basically made it better for applications that could come into contact with some type of radiation, such as single event upsets and that sort of thing. And then Flash EEPROM, these are Microsemi and Lattice had some products and still have some products that provide for lower power operation, faster programming, and they're typically smaller in size. So for the sake of this discussion, development environments, we'll talk about Xilinx and the Intel Altera tools, since they're the two leaders in this SRAM-based FPGA market. So Xilinx current tool set is called Vivado. Previously, their tool set was called ISE. And what the tool set allows you to do is design entry, then design synthesis, implementation, programming of the FPGA, verifying that the FPGA is working. And they also have tools, an SDK, software development kit, so that you can integrate and debug your code for your Zinc and Microblaze processors. Intel and Altera, they use what they call Quartus Prime, and it's very similar in that you do design entry, logic synthesis, place and route, and then timing and power analysis, and finally device programming. In part 2, we will get into the details of the Xilinx Vivado tools as we go through an example design. So here are a handful of coding methods that engineers will use to develop their code to use on an FPGA board. VHDL is very high speed IC hardware description language. So in the past, systems use this language to describe and verify before synthesis. And this code is portable so that you could take it from one FPGA platform to another fairly easily. Verilog HDL, commonly referred to as IEEE 1364, is used for design and verification of digital circuits at the RTL level, RTL being register transfer level. And it's also used for verification of analog and mixed signal circuits. RTL basically is register transfer level. It applies to pure combinational logic, and it provides for a schematic diagram as the output. There's also a coding method called high-level synthesis, which uses C and C++. And this allows you to transform an untimed or partially timed functional code into a fully timed RTL. So there are a couple of companies that specialize in logic synthesis tools, Synopsys being one of them that comes to mind, but there are others out there. OpenCL, that stands for Open Computing Language, and sometimes that's used for doing code for FPGAs. It's basically a framework for writing programs across many platforms, and it's based on C99 and C++11. As I mentioned, the design tools for Xilinx FPGA. Xilinx has the Vivado design suite. So they have a high-level synthesis tool. They have a IP, intellectual property integrator. They have what they call their Vivado simulator. And then they use ChipScope Pro Tool Debugger. And this debugger allows you to debug or program over a JTAG interface. And you can check out timing, you could check out code, that sort of thing with this ChipScope debugger. Typically, you program your FPGA over a JTAG connection through a quad SPI flash, through USB or micro SD, secure digital. And this programming comes through the bitstream file. There are other tools that support Xilinx. There's a company called MathWorks that offers MATLAB and Simulink. And these tools allow you to model the hardware architecture at a system level and then program, simulate, and debug your FPGA. Then there's National Instruments, which has LabVIEW, and they have a tool called FPGA module, and this allows them to program their FPGAs that are specific to the National Instruments FPGA boards. So why use FPGAs? I broke this down into some technical reasons and some business reasons. I think one of the best reason to use an FPGA is because it is reprogrammable and it allows your application to, if the specifications change, if the requirements change, it allows you to reprogram these multiple times. Another performance is if you're trying to do many operations in parallel, an FPGA is a very good tool to use. If you have an iterative design approach, you try this, it doesn't work, you try this, and it doesn't work. Another reason to use FPGAs. If you're trying to do all your processing on a chip with these SoCs out there, you can do a great deal of processing, taking inputs, processing them, sending outputs, all on the same chip. I like the reason that people use FPGAs because it allows you to fail many times, and basically this allows you to learn and gain experience so that you're successful in the future. Another reason that people like to use FPGAs is you can replace end-of-life products very easily, and flexibility is another key reason for using FPGAs. One of the typical business reasons is that it reduces your risk of development, it provides for shorter lead times, and you can use the same FPGA for many different applications. So your engineers, both hardware and software people, once they build up their experience level using a certain family, whether it's Xilinx or Intel, they have this experience that they can fall back on, and a new application comes up, they can get to market very quickly and reduce the risk in the development. FPGAs are very cost effective for lower volume applications. So if you were going to be building 1 million systems of something, you probably wouldn't be going with an FPGA into production. You might develop with an FPGA and then try to move that into a standard cell design or try to move that into a custom design and optimize for either lower cost or higher performance. One of the key business reasons that people love to use FPGAs is the lower non-recurring engineering costs. The precursor to field programmable gate arrays was gate arrays, and typically there was a mask interconnect fee, typically anywhere from $3,000 to $10,000 a mask. So people would spend on the order of $20 to $30, sometimes $50,000 to $60,000 to get a gate array developed. Here, you pay a couple $1,000s in some cases for a board or a chip, and you can reprogram it many times. So it's much more cost effective, and it lowers the non-recurring engineering costs that your company will have to bear. Typical applications for FPGAs. There are so many of them, and it really depends on the complexity of the FPGA. But these are some typical applications that we see people using FPGAs for: protocol conversion, missile simulation, running certain algorithms on data. For example, you have to do some baseband to high frequency conversion, or doing some down conversion. So there are up converters, down converters. Another application is video processing or enhancement to video. Radar applications typically require analog to digital converters and digital to analog converters, and typically in the middle of that you have an FPGA that does all the processing of the waveforms coming in from the radar. Hardware in the loop is another application that people use FPGAs extensively. Sensor data acquisition. If you have a variety of different serial data, TTL data coming in, maybe LVDS, maybe CMOS, it can take all these inputs and you can process this data on chip and then send it to where it needs to go. A system on a chip, SoC, for example, the Zinc UltraScale has a couple of different RISC processors with multiple cores. It has a variety of logic, and it has a variety of memory and DSP resources. So you can do a great deal of processing all on one chip. For doing bus interfaces, for example, VME and PCI Express bus interfaces, there was a VME bus interface chip called a TSI 148 that went into life. We worked on an FPGA, and we now implement that bus interface with an Arctic 7 on our VME processor board. Timing signal generator, that's another typical application. Since timing is very critical on an FPGA, you're allowed to do things in a deterministic manner, and you're able to be very precise and get very low skew with your timing signals on an FPGA. Waveform generators. For example, if you want to create some special sine waves, if you want to spoof things, if you want to make different waveforms change their characteristics, FPGAs are used in that manner. Software-defined radio is another application that is and has been used quite extensively with FPGAs, primarily because they could be reprogrammed in the field, in circuit, and that you could change the characteristics and support a variety of different radio frequencies with the FPGAs. I'm going to give you a brief overview of some of the Acromag FPGAs that we support in both PMC and XMC form factor. We started in the FPGA business back in 2002 with the Vertex 2. That has gone end of life, but from this chart you can see that we still support Vertex 4s, Vertex 5s, Spartan 6s, and the Kintex 7 and the Arctic 7, and we will continue to support these FPGA boards far into the future. We also have these tables that show what a Arctic 7 and a Kintex 7 look like. This table primarily shows that we have typically 3 versions of our FPGA board. We have a front I/O version that uses AXM modules, which I'll get into in a minute, but these are a variety of I/O that are off the shelf that you can plug in and screw down and interface into your base FPGA board. We have a dual SFP Plus version on our Kintex 7 FPGA family. And then all of our FPGAs come with a conduction cooled variant that has rear I/O. The table in the middle shows the logic cells. Our Arctic 7, we have a 200T for the largest that we support. And you can see that it has 215,360 logic cells with 740 DSP slices and 13,140 kilobits of memory. As you go up and to the right, you'll see that the XM, the K410, the 7K410 has over 400,000 logic cells, and it is the largest Kintex 7 FPGA that we support. The AXM modules on the bottom table, what this is, it's a pluggable I/O module that allows you to use our base FPGA board. It could be a 7A, a 7K, a Spartan 6, a Vertex 4, Vertex 5 FPGA card, and you plug these AXM modules into the front I/O, and it allows you to provide low voltage TTL, serial or a combination CMOS and serial or low voltage differential signaling. And we also have a couple of variants that provide for analog inputs and analog outputs. And then our AXM-EDK is a EDK that's primarily used for debugging and development, and it includes a JTAG port on it. Here's a block diagram of our Arctic 7 and our Kintex 7 FPGA. On the left, you can see there are 3 connectors that our AXM I/O module would plug into, and this provides an interface into the FPGA. And then you have the FPGA with the parallel flash resource for programming. You have quad DDR3 SDRAM for other storage. And then we have interfaces to the P4 connector, P15 connector, and P16 connector, which are the XMC connectors. So in often cases, you can have front I/O coming into the FPGA, and then you have a variety of rear I/O going to these connectors. So you can get I/O into the FPGA, process it, and get I/O out of the FPGA very easily. Below is a picture of one of our FPGA boards, and we typically will host these on carrier boards, and I'll get into that in a moment. But I wanted to introduce you to the AcroPack A7-50X family. Now, where the PMC and XMCs have removable AXM module I/O capability, the AcroPacks have dedicated I/O. And we're using an Arctic 7 50T FPGA. This Arctic 7 FPGA manages the PCI Express interface on one side, and then has the I/O buffers on the other side, and it can be either a 48 TTL or 24 serial, or a combination of TTL and serial, or 24 low voltage differential signaling I/O. The resources of this AcroPack module are 52,000 logic cells and 2,700 kilobits of memory with 120 DSP slices. Essentially, 50% of this FPGA is reprogrammable by the user. The other 50% of it handles the PCI Express bus interface, the flash interface, and DMA interfaces. So our AcroPack carriers, every AcroPack FPGA board or AcroPack I/O module requires a carrier board. This is a list of our PCI Express server carrier boards. We have a single carrier low profile that's a PCI Express by 1, and then we have a dual carrier that's a PCI Express by 4 connection that will host 2 AcroPack modules, and then we have 2 quad carriers. One is a full length and the other is a 3/4 length that are both PCI Express by 4 carriers. We also make a 3U VPX carrier, a 6U VPX carrier, a XMC carrier that hosts 2 AcroPack modules, and a 3U compact PCI serial carrier board that will host our AcroPack modules. So future topics that we will talk about in part 2 of 3, we will put together an example FPGA design. We'll show this using the Xilinx Vivado tools, and then we'll talk about the advantages of Acromag FPGA boards. And part 3 of 3 will be discussing the Zinc UltraScale architecture and its advantages in the market. At this point in time, I'd like to thank you for attending, and I'd be happy to answer any questions that you might have.
Thanks, Greg. Yeah, we'll open up the Q&A section right now, and feel free to use the chat box as well if you have any questions. One of them that has come in, Greg, what are advantages to AXM modules versus fixed I/O on PMC and XMC FPGA boards?
Yeah, so the primary advantages with the AXM I/O modules is that you can use the same base FPGA board and swap out a variety of different I/O cards. So if you have a variety of testers that you need an FPGA, and some of these inputs and outputs are low voltage differential, some are analog, some are input, you can get experience with the same baseboard, and you could swap out and use a variety of different AXM I/O modules. That's one advantage.
Okay, very good. Another one came in here. Can you explain the difference again between FPGA and CPLD?
Yeah, so CPLD is complex programmable logic device. It is typically a device that is much smaller in size. It's much less expensive. CPLDs were around, PLDs and PALs were before the CPLD, and they're typically a little bit faster to program. They're non-volatile in most cases, so that once you program them, you don't lose them upon power down, and they're still used quite a bit today. They're not as complex, and you typically will find a lot of CPLDs in applications that are consumer or industrial oriented.
Okay, very good. Another one here. What are the differences between the AcroPack you talked about and XMC FPGAs?
Yeah, so AcroPack modules, they are built based upon the mini PCI Express form factor that has been extended to allow an additional 100-pin Samtech connector on the bottom of the board. So basically, AcroPacks are smaller, they're used on a carrier board, and the carrier board routes the I/O. So in some cases, you can't get as many I/O on an AcroPack as you could get on a PMC or an XMC card. But what you can get is very high density. For example, you could, in an XMC card, you could use 2 AcroPack modules, and you could use an AcroPack, one an FPGA, one an analog input or analog output, and it just gives you more flexibility. with the AcroPacks.
Okay, very good. Question here about DCMs. What are they, or why are they used?
Yeah, so digital clock managers, as I mentioned, when you're interconnecting the programmable logic blocks on the FPGA, you want to make sure that you have clocks that can handle wider loads and reduced skew, so your timing is better and predictable. So digital clock managers are used quite extensively on the FPGA for performance enhancement as it relates to timing.
Okay, thank you. I've got another one that just came in. Do you know why the industry is moving to PCIe for so many on-chip applications?
Well, PCIe, right now, manufacturers are coming out with Generation 4 PCIe. And Gen 1 was 2.5 gigabits per second. So very high speed serial as compared to PCI, which was 66 megahertz, 100 megahertz. And I think the future is PCI Express just because of its speed, its serial nature, and it is just a standard that more people are pushing for high performance. And from a cost performance standpoint, it's very effective.
Very good. Well, I'm waiting to see if any other questions come in. That's all I've got so far. So I'll just give it another second here and see if anything pops up. And it looks like we're winding down. So I think I'll take this moment to say thank you here. Oh, hold on, stand by. One question, another question coming in. I'm gonna let him finish his sentence here. So this is someone here that's talking about having trouble with VME and PCIe interface on a processor board. They're having trouble with that. Is there anything you can speak to with that little bit of information? Perhaps we could connect you guys after the call.
Yeah, I'd be happy to talk with them after the call. Just in general, typically your processor, if it's a VME processor board, it's going to have a PCI Express interface to the PMC, XMC sites on that board. So if you use an XMC, it'll have a direct connection to the processor through the PCI Express bus interface. But then if you're taking the I/O from that XMC and running it to the VME bus, it has to go through a bus interface translator chip, similar to what I mentioned, the Arctic 7 FPGA implementation on ours. But I'd be happy to discuss that offline.
Yeah, absolutely. He's sent in a little bit more context here. So I think we can get a hold of him after the call and dive into this a little bit deeper. It looks like he could definitely use some help. So that's really what we're all about here, getting Acromag and our partners involved to help solve problems. So we really appreciate you, Greg, for taking the time to provide your expertise, as well as everyone in attendance. Really appreciate you taking the time to listen in, and just based on the feedback that we're getting, we'll continue to do our Tech Tuesdays. So continue to visit Vic Myers Associates vicmyers.com/events. If you'd like to see the upcoming Tech Tuesdays, look for our emails as well. And also, you can be in touch with any of the local reps. Our website has all the local contact information for all your states. So feel free to check it out there. And then we'll also get a replay out via email. So look for that link tomorrow, and you can pass on this information, the attachments in the meeting, as well as follow up the questions that we have here. So once again, from Vic Myers Associates and Acromag, thank you all for attending. We appreciate you. Stay safe out there.